Okay, we're going to start section 4.5 with an exploration of the relationship between a derivative using the chain rule and then its integral. So if we're trying to take the derivative of 2x minus 5 to the fourth power, using the chain rule, we put the 4 out in front, 2x minus 5 to the third, so that's the derivative of the outside function, and then we're going to multiply it times the derivative of the inside function. So using the knowledge that we have that the derivative and the integral are inverses of each other, if we do the integral of this answer that we got, so the integral of 4 times 2x minus 5 to the third times 2 with respect to x, so dx, that should equal 2x minus 5 to the fourth, right? Well, let's look at this one. If we take the derivative of 2x minus 4 to the fourth, it should be 4 times 2x minus 4 to the third, and then times the derivative of the inside, which is 2. So let's write that integral. The integral of 4 times 2x minus 4 to the third times 2 with respect to x should be 2x minus 4 to the fourth plus c. This 4 and this 2 could have been multiplied together, so that integral could look like this. Or even that 8 could be out in front here. So when we're integrating something like this, the way it looks right now, it doesn't look like we should be able to integrate it because that 8 should have been out in front here. And we don't have a rule for how to integrate 2x minus 4 to the third power. Right now, if we were trying to integrate this, we take that 8 out. The only way we know how to integrate this would be to multiply out 2x minus 4 to the third power all the way, and then integrate each piece, and then multiply each answer times 8. But what we're going to do is learn a rule called the product rule, or called U substitution, that will help us find the integral of something that is set up as a quotient. Let's see if we can further explore this. If we do the derivative of 2x to the fifth time to the 10th power, the derivative would be 10 times the 2x to the fifth to the 9th power, and then times the derivative of the inside. And then again, if we integrated that, we should get back to the original. So we'd have 10 2x to the fifth to the 9th times 10x to the fourth with respect to x. That should equal 2x to the fifth to the 10th plus c. So notice this main part here, is now to the 10th power, it was to the 9th power, and this main part here in the integral was to the third power, now it's to the fourth power. Up here, this main part was to the third power, and now it's to the fourth power. So the main part, the power increases. If we're trying to find a generalization of this, the power increases. And notice that this integral of 4 is not there, because that was the power that we put out in front for derivative, so it's not there in the answer of the antiderivative. Or likewise, this 10 came from this 10 that we put out in front, and now it's not there when we integrate. And where does this come from? Or this 2? Or this 2? So all the pieces are there from the derivative. We have our main part, put that 4 out in front, subtract 1 from the exponent, and then multiply by the derivative of the inside. When we integrate, all those parts have to be there. We have to have the derivative of the inside. The derivative of the inside has to be there in the part of the integrand. We have to have the main function in the integrand, but the power of it will be 1 lower than here. And we have to have that number out in front that we multiplied by when we did the derivative. So, a conclusion about a possible product rule for integration. The integral of some function to a power times du. Now this du is a big deal here. So the integral of u to the n du is you add 1 to the exponent, divide by the new exponent. Because remember, this 10 wasn't there anymore, this 4 wasn't there anymore. So when we added 1 to the exponent, we divided by the new exponent. Those canceled out, and we had a 10. But also we need this derivative. So this, not only are we trying to find a possible product rule, but also a possible chain rule for integrating. So using composite functions. So if we have the integral of some function to a power, and then this is like a times sign here, this might be a whole function because it might be the derivative of the inside. Then the integral of a function to a power, du, is just that original function, add 1 to the exponent, divide by the new exponent, plus c. It looks basic here, but what we're going to use this for is things that are a little more complicated than just u to the n du. I'll show you what I mean. So if we had this function, let's do this one, the integral of, I'm sorry, not that one, 10x to the 4th times 2x to the 5th to the 9th times 10. What we're going to do is think of this as u, so it's u to the 9th, and then this whole thing here, 10 times 10 to the 4th, all of that is going to be the du part. So we're thinking of this as our main function because it's to the highest power, and then all the other stuff has to be part of this du. So we're trying to rearrange our integrand that looks like a product right now into a main function to a power, and then the rest of it is going to be part of our dx. And then once we get that, we can use this formula. It'll make more sense after I do some examples. So here are your steps. Choose u. To choose u, you choose the inside function that's raised to a power, or any part of the function that's raised to a highest power, because you may have two functions raised to a power. So choose the one that's raised to the highest power. We could use this for a function, for a quotient rule for integrating. So you might want to choose the denominator if we have a denominator that has a variable in it. We could also choose a function that's a derivative of the other function. So in the situation where you have a product, you would want to choose one function that's the derivative of the other function as u. Choose the function that is inside the square root, or choose the function that is inside of a trig function. Those are some hints for choosing u. Most often, we're going to use these three here. Once you choose u, find the derivative of u with respect to x. Solve that little equation for dx. Then we're going to substitute whatever u was equal to and whatever dx was equal to into the problem. Then we're going to use this integration formula here. We should also simplify here. If there is any simplifying that needs to be done, that should be done in step 4. Integrate, and then back substitute. All right, let's go through all those steps. So here's a problem. We have integral of 3x squared times the square root of x cubed plus 1 dx. First step, notice that we can't simplify this. We can't multiply this in, we can't do square roots, so we know we have to use this thing called u substitution. Our first step is to choose u. Going back to our hints, do we have an inside function that's raised to a power? Kind of, because this is really 3x squared times x cubed plus 1 to the 1/2 power. Right? So we can use that. Also, it qualifies here. So both of these kind of mean the same thing because something that's in the square root is to the 1/2 power. So we've chosen our u. U will be x cubed plus 1. It's the inside function raised to a power. Step 2, find du dx. So we're going to take the derivative of this u. X cubed, derivative of x cubed is 3x squared. Derivative of 1 is 0. That's step 2. Step 3, solve for dx. We want the dx by itself. So you're going to multiply both sides by dx. So du equals 3x squared dx. Still haven't solved for dx, we're working on it. Divide by your 3x squared. So dx equals du over 3x squared. Now if you don't follow these steps, you probably won't get the answer right, so please be careful to follow the steps. That's step 3, solve for dx. So you do have to think about the du over dx as two separate variables, du divided by dx. We've probably never thought about it like that before, but to solve these equations you have to think about du divided by dx as two separate variables, not a whole derivative. Step 4, substitute what u equals, so that's this, with the letter u. And substitute what dx equals, which is this, in for dx. So let's do the substitution. Integral of 3x squared times u to the 1/2. So we've substituted, instead of x cubed plus 1, we're putting the letter u in there, right in there. And instead of dx, we're going to put du over 3x squared. You've probably never even thought about this dx there, but it always goes with the integral, and it is part of solving integrals when you have to do a little substitution. So notice this didn't get replaced with anything. That's good. Notice it cancels when we do the simplifying step, which is part of step 4. Once you're done with step 4, all x's should be gone. They should either be replaced with the letter u, or they should have canceled out. If they don't, we'll have more steps in a couple days, but right now, that's what we're left with. Integral of u to the 1/2 du. If you don't have all of your x's canceled out or substituted, you made a mistake in steps 1, 2, or 3. You either chose the wrong u, you took the derivative incorrectly, you solved for dx incorrectly, or you substituted incorrectly. One of those steps was wrong if when you're done with step 4, all of your x's are not gone, because you should end up with something that is just u to a power and then du, because then we can use this. We have u to a power du. Then we can integrate using this formula. If you don't have u to the n du at this step, you cannot use that formula. You have to go back and figure out what you did wrong here so that you can use the formula. You can only use a formula if this matches exactly. So now we're on step 5, use the formula. Integration formula by u substitution. So integrating that, we add 1 to the exponent, divide by the new exponent. Dividing by 3/2 is the same as multiplying by its reciprocal. And then plus c. And then we back substitute. So put back in what you started with for the letter u, because your final answer has to have the original letter in it that you started with. We started with x's, so now we have to have x's in our final answer. Let's do another example. So we've got the integral of x times 4x squared plus 3 to the 3rd. If you wanted to, you could cube all this out and then distribute the x in. And you'd have to do it in that order. You cannot distribute an x into something that's raised to a power. But that's a lot of work. Our substitution will be a little bit easier. Our first step is choose u. U is the thing that's raised to the highest power. So that's your 4x squared plus 3. Step 2, take the derivative. And don't just write u prime, because we want to solve for dx, and if you just write u prime, you don't have a dx to solve for. So the du dx notation is going to be very helpful for us here. Derivative of u is 8x plus 0. Step 3, solve for dx. So you multiply both sides by dx, and then we have du equals 8x dx. Divide by 8x. Dx equals du over 8x. Step 4, substitute. Keep the x where it is. Replace the 4x squared plus 3 with u. Keep that power the way it is. Replace dx with du over 8x. Notice what cancels. The x cancels. That's good, because after this step, we better not have any x's left. But we do have this 8 here in the denominator. So technically we have u to the third times 1/8 times du. That 8's in the denominator. Constants can go out in front when you integrate. So before I integrate, pull out all constants that are multiplied or divided. Then this part looks exactly like the formula. So we can take the integral of u to the n du by adding 1 to the exponent, dividing by the new exponent, and then taking that answer times 1/8. Simplifying, we get u to the 4th over 32. And then back substituting. Our final answer is u to the 4th, and u was 4x squared plus 3 over 32 plus c. Here we've got two things that are raised to the same power. They're multiplied together. It's like this: secant squared x times tangent squared x. We can't multiply them together, so we've got to choose one of them as u. Going back to our list of things to choose for u, they're both raised to the same power, so we can't do an inside function raised to a power. We've got two of them. We can't pick the one raised to the highest power because they're both the same. We don't have a denominator. Is there one that's one function that is the derivative of the other function? Well, let's see. What's the derivative of secant? It's secant tangent. That's not tangent. What's the derivative of tangent? Secant squared. So choose u as tangent. Not tangent squared, just tangent. Because remember what else this means. This means secant x squared times tangent x squared. So this is our inside function. Oh, I don't know what letter that was. Inside function. That's the inside function raised to that power, and the reason we're choosing this one as the inside is because its derivative is secant squared, which we hope will cancel when we solve for dx. Step 2, find derivative of u. Secant squared x. Step 3, solve for dx. Solve for dx. So multiply by dx on both sides. Divide by secant squared to solve for dx. Now this is not the way the book teaches it, and it's not the way CalcChat is going to show it, but I have found that it is the easiest way to integrate. It causes the least amount of confusion for people. So please follow my examples and not what CalcChat says. So we have the integral of secant squared x, which we're not going to replace. We're on step 4 now. Substituting, so u to the second, because u is tangent, and then dx is du over secant squared. Because we chose u as tangent, when you took the derivative of it, you end up with a secant squared x in the denominator. That's going to cancel. That's good. After this step, we should not have any x's left at all. We should just have constants and u to a power du. Now we can integrate that. You add 1 to the exponent, divide by the new exponent, plus c. Back substitute, u was tangent, so you could write it like this, but mathematicians are lazy. They would always write it like this. So there's your final answer. We started out with a product. It looked like a product, but it really was this. So we don't really have a product rule. It's a u substitution rule, but it works for products, quotients, and chain rule, composition of functions. Let's do one with a product, or a quotient. Now this quotient actually can be rewritten before we integrate it. two ways to go from here. So we changed our square root to t to the 1/2. You can either split it up, and you can only split up fractions if the denominator is a single term. So you could do that, and then reduce it. When you reduce, you subtract exponents, so that's going to be t to the 1/2, and 2 minus 1/2 is t to the 3/2. Ta-da! Now we don't need to do a quotient rule or any kind of weird rule. So always be on the lookout for simplifying first before you try to integrate or try to apply the u substitution, because here we can just add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent, plus c, and then the book's going to get a common denominator. So a good denominator here would be 15. So we'd have 10 t to the 3/2 plus 6 t to the 5/2 all over 15. The book is also going to factor out the greatest common factor. So these both have a 2 in common and a 15 in the denominator, and then t to the 3/2, they both have that. So if you take out a 2 from here, you'll have a 5. If you take out t to the 3/2, you don't have any t's left there. And here you take out a 2, you'll have a 3 left. And t to the 5/2, if you take out a t to the 3/2, you subtract those and you'll have t to the 2/2, which is just 1. So that will be the final answer you'll see in the book. On a test, you can leave it like this, but if it's multiple choice, you better know how to get from here to here. So if I were working on homework, I would make sure I continue to practice getting from here to here every time I did problems like this. But on a test, when you're trying to save time, stop there. That's fine. All right, another way to think about this, instead of going here and splitting up the fraction, is you can bring up that t to the 1/2 like that, and then just distribute it in. So you add exponents here, so that's t to the 1/2, and you add exponents here, t to the 3/2. So either way, you don't have to use any strange rule, any u substitution rules. Keep your eye out for quotients that you can use simplifying to get it into a form where you don't have to do a u substitution. Another problem that will be on your homework is to solve a differential equation. Solving a differential equation, the goal is to get rid of the derivative and end up with a y equals equation. So we want to separate the dy and the dx, your first step. Separate dy dx. So you end up with dy equals 10x squared over the square root of 1 plus x to the third dx. So step 1, separate the y's and the x's. Step 2, integrate. If you want to end up with a y and you have a dy, you're going to need to integrate, because integrating and differentiating undo each other. What's the integral of 1 dy? Just y. So the left side's done. We're there. We've got y equals. Now we just have to figure out this side. Here we have a quotient rule, and unfortunately we can't simplify it. Or fortunately, because I get to show you how to use the u substitution. The u substitution, remember to choose for u, we're going to choose either the denominator or what's inside of a square root or the biggest group that's raised to a power. All of that leads us to say that our u is going to be 1 plus x cubed. Take the derivative. It's going to be 3x squared. Solve for dx. You're going to multiply by dx on both sides, and then you're going to divide by 3x squared. So we'll have du over 3x squared. Oops, I've been writing it the other way, so I'm just going to continue to write it the other way so it's consistent. So du over 3x squared equals dx. Then substitute. So we still have the integral sign. We still have the 10x squared. In the denominator, we have u inside of a square root, but I'm going to change that to u to the 1/2. And then we have dx, which is du over 3x squared. So rewriting that, I have the integral of 10x squared over u to the 1/2 times du over 3x squared. Now we're going to simplify, and we want to cancel everything we can. After this step, remember all of our x's have to be canceled, not necessarily the constants. So that constant we can pull out, the 10 and the 3, the 10's on top, the 3's in the denominators, keep them where they are, and I have 1 over u to the 1/2 du. Now that does not look like u to the n du. I can't use the simplification or the formula until I have u to the n du, but I can bring this u up to the top. So y equals 10/3 times the integral of u to the -1/2 du. Remember, if you have a variable in the denominator, you can bring it up to the top by changing the exponent to negative. Now we have u to the n du, so I can integrate. Y equals 10/3 times u to the, add 1 to the exponent, divide by the new exponent, so that's the same as multiplying by 2, plus c. So y equals 10/3 times 2 is going to be 20/3. U to the 1/2 is the same as square root of u, so I'm back substituting, plus c. So there's my final answer. So we solved the differential equation. We started with a derivative, which is a differential equation, anything with a derivative in it. Separate the variables by multiplying by dx. Integrate to get rid of the d part, the derivative part. And on the right side, we had to integrate using u substitution. Notice how that u substitution helped us integrate a quotient. So the u substitution works for quotients, products, and composite functions. There's your homework, page 306, 1 to 41 odd.